given this current trend, we have to look at the resources that we have. The unlicensed spectrum that we use in the 2.4 gigahertz and in 5 gigahertz bands, they are very limited in number. Even though we can say that there are up to 24 non-overlapping channels in the 5 gigahertz band, most of them, a significant number of them are used for radar and some other purposes. So the actual numbers that are being used for regular wireless local area networks is less. So we have a lot of resource constraint. So this creates a need for adaptive and automatic radio resource management strategies. A typical deployment scenario for power control would be this. This is a multi-dwelling unit scenario, like an apartment building or a hotel. A satellite IP gateway can convert satellite TV signals into IPTV format. We can send it over the gigabit Ethernet backbone, and we can use 802.11n APs and IP set-top boxes to stream multiple high-definition video. As you can see, some stations for IP set-top boxes experience good channel conditions compared to the others. So this gives us room for improvement where we can use a lower transmit power to stations that are experiencing good channel conditions and a higher power for those that are not experiencing good channel conditions. So now the fact remains that the lesser the transmit power we use, the greater the channel reuse, or in other words, the smaller the spatial interval needed to reuse the same channel. But there are some constraints and challenges. The constraints here are placed by the content we are dealing with. For example, in our scenario, we talked about high definition video transfer. So throughput and frame loss rate requirements are key in with such content. And then the challenges are varying channel conditions. As I said, some stations might experience good links, some others bad. So it should be adaptable. So the need here is to leverage the fact, taking into consideration the constraints and the challenges. Okay, any good transmit power control algorithm needs to take certain factors into consideration. We already raised our objective. We want to use the minimum transmit power possible to achieve successful transmission at a target data rate. I'll detail as to what the target data rate in the next few slides. So given this objective, we are allowed to operate with certain preconditions. The preconditions being incremental deployability. We don't want to make significant changes to the fundamental 802.11 and that would ensure that it can be deployed amidst non-cooperative nodes or nodes that don't use transmit power control at all. Second, it should be realizable in practice. There are a number of complex transmit power control algorithms that can easily pinpoint the optimum transmit power that we need to use, but they don't take the system level limitations into account. So a good transmit power control algorithm should take those limitations into account as well in its design. And finally, a good algorithm should be able to tackle hidden node and asymmetric channel access problems. These are usually aggravated by the use of power control. So let me explain what they are in the future slides. So coming to the choice of our target data rate, a specified target data rate is the minimum speed at which you want to guarantee. So in our case, the maximum data rate supported by 802.11n devices is our target data rate. We want to ensure that by doing power control, the power control is not going to adversely affect the rate or the data rate being used by the system. So that's what the target data rate means. And it's MCS 15. By MCS 15, what we mean is modulation and coding scheme 15. It corresponds to 64 QAM and 5/6 convolutional, 5/6 convolutional code rate. It gives 130 Mbps with 2 spatial streams because 11 devices which we used had 2x2 minor. So the maximum data rate that was possible was 130 Mbps in the regular 20 MHz band. Then coming to the granularity of power control, this is closely tied with
what does MCS 15 mean again?
Modulation and coding scheme 15, which corresponds to modulation from 64 QAM and 5/6 convolutional code rate. So that gives
So your target data rate is always 130 megabits per second.
yeah, the target data rate is 130 megabits per second. So we want to ensure
Even
that
if your video only requires 10 megabits per second.
yeah, the video might require a particular video stream might require 10 megabits per second, but the target is always 130 Mbps. The physical data rate target is always 130 Mbps.
Okay.
Okay. It will get clearer as we proceed with the explanation for the algorithm.
I don't particularly agree with the reason for the choice of target data rate. You say that the reason is the smallest airtime corresponds to minimal interference, but if I am transmitting at full power, I cannot have parallel streams. It's not obvious to me unless there is some analysis that you do to show that the highest rate being chosen every time for any link will lead to minimal interference.
Highest rate.
Like if I always choose 54 Mbps for any link I am servicing,
Okay.
but I set my power so that I can achieve 54 Mbps. It would mean very high power for nodes that are at the edge of the cell, let's say, right? When I use very high power, I basically say that I cannot have any parallel streams, right, because of interference again.
Yeah.
So there are no parallel streams, all streams have to be sequential. So I'm not sure that by choosing the target data rate, you're minimizing interference. Like, how do you say you're minimizing interference?
Okay, so empirically we found that in 802.11n devices, the range is huge because of MIMO, and there is also a third antenna for diversity in this case. So the range is huge. What we found that for typical deployment scenarios, for typical distances between AP and station inside home, it's like even for distances as far as 70 feet line of sight, we could get 130 Mbps at lowest power possible. So that was the reason why we chose 130 Mbps. True, power control could even provide further gains if we do rate control along with power control. But for typical deployment scenarios where the distance between AP and station is usually small, which can sustain maximum data rate, we chose to use maximum data rate as the target data rate.
So in these multi-dwelling units, you mentioned you will not have any distances greater than 70 feet.
Between AP and a station, 100 feet would be the maximum, I would say. Because each house has an AP.
But what about the station in the next unit that's connected to another AP?
Next unit that's gone. Other.
I think he's talking about intercell interference in Wi-Fi.
Yeah, the idea is to reduce intercell interference. We are talking about, say, in your case, AP in a house, in a dwelling unit, the distance between an AP and a particular station can be a maximum of 100 feet. That's what I'm
Yes,
trying to say.
but I guess what we're saying is if there are other stations around, which may be connected to other APs, think of the next unit in your apartment, which has its own AP.
Okay.
You might be able to reduce interference even further if you were to lower the rate and lower the power even more.
Okay. Yeah, I get it.
So we disagree with a statement that the smallest airtime always corresponds to minimal interference.
I think there is a conservation law here because the total power, interference power is going to be the same whether you transmit at lower power and longer period versus more power and shorter period. So unless you actually reduce the data being transmitted, there is more or less a conservation of interference that occurs in the water rate. But I think
if you're considering that all stations are close enough in interference range, I think it depends very much on the spatial distribution of stations. You can find scenarios where this is true and scenarios where it's not true. Where you're much better off operating at the lowest rate and lowest power.
no, you can't have the lowest rate and lowest power. I think what he's saying is not fully justifiable. He made a choice of the highest rate. But my point is that if the rate, and if you look at both power and rate, the product can be constant. It's not dependent on
For lower rate, the sensitivity requirement might be like for which you would have to transmit at a higher power. That again would prevent simultaneous streams.
I
It
think
is,
we
if
did.
you lower your power, you can get spatial reuse at some point.
That's
So
right, but
you can,
spatial
you can,
reuse,
you can, you can take up all the time you want and do not affect another station.
the spatial reuse depends on both the amount of time as well as the power that you transmit at. So the average power received, you cannot change that because simply by going to, but what he's pointing out is that within the cells, when you're target data, when you operate at the highest rate, you create the least amount of traffic interference within a given cell. So that's
That,
what
that part we agree on. If everybody is close, this is.
But I think for the-
But if there are other stations around, it's not optimal.
Well, I have two questions. First, when you say minimal interference, what do you mean? Do you mean in terms of time?
In terms of time.
Okay, so in terms of time, not in terms of overlapping energy.
Yes.
So I think it makes sense. If you transmit a very short time, it's less likely that there is that there is interference. In terms of
So
time,
I think he just made a pragmatic decision to try and use, that's just a heuristic, there's no optimization involved, he just chose that.
the second question is that under 30 megabit per second, is that a raw data, is it raw rate? It's a kind of air rate, meaning
The MAC rate, as in,
is it a
it's
physical
the physical
rate? It's a constant physical rate.
Yeah.
But the forward error correction schemes will trade off, will add more redundancy if needed, so the actual data rate will be lower, even if the physical raw data rate is 130 megabit per second. So you are reducing the rate at the application level.
at the
What is that rate? It's the physical rate.
This is the physical rate at the time talking.
So doesn't mean that you're always transmitting at 130 megabit per second in terms of data.
No. I don't worry about rate control at all in this procedure. All I'm trying to ensure is that I provide the conditions such that the maximum transfer at maximum data rate can be sustained. We are not worried about rate control part at all. We just want to make sure that we don't affect it adversely.
When you say rate, what is this rate? Where is this rate?
This is the 5 data rate. 130 Mbps is the based on the modulation coding scheme and a corresponding error correction code.
So if the forward error correction scheme needs more redundancy, then 130 megabit per second will stay the same, but the data rate.
No, that is for a code rate of 5/6. That is, this number corresponds to 64 QAM and 5/6 convolutional code rate.
So that the coding is not changing.
Yeah, it's not changing. If you want to change the code, then that will correspond to another modulation coding pair, which will correspond to, say, either MCS 14 or some other data.
Yeah, but then the question is, and this is very much correlated to what we were saying before, why not attacking this problem, I mean, looking at joint, rate control and code, coding and power?
That's very complex. In practical, you cannot do that.
Why?
Because whenever, I move a little bit, everything changes. So it takes a lot of time, you do the measurement, right? After you measure, then you change your rate. So it never get real-time feedback.
True, but that's suboptimal by
Theoretically, you can do it. You can come up very nice equation, you can do these things. So that in practical, no.
But they also have another constraint of not wanting to change the cards, and
Right.
so that's a big constraint. So really cannot change anything on the file layer.
So,
Are you assuming a party varying channel?
I'm sorry,
Is your channel party varying or is it kind of constant?
it's a typical indoor wireless channel. So it is, the way I see the variation is in terms of RSSI, and there isn't significant variation. Next is the granularity of the power control. We usually effect power control changes using ioptical pulse exposed by the device drivers. Atheros provides 32 different power levels, and we choose to use only 15 different power levels from 1 to 15 dBm. And while discussing the implementation, it becomes more clearer as to why the choice is made. Okay. The next important thing is the trigger for power control. by trigger, the basic what we mean is the basic parameter that we use to decide on the transmit path control to use. Before trying to understand the triggers that we use, we need to understand the 6 interference scenarios. These are the 6 possible scenarios that can occur between between a pair of links which are operating transmit path control. Again, a detailed study of the probability of the occurrences of these has been made by Kishore, who was in lab earlier. Again, this work is derived from his. So, the first scenario, A, represents perfect spatial reuse. I would like to point out that a dash or a dotted line from a transmitter 2 to transmitter 1 means that transmitter 1 is in the carrier sensing range of transmitter 2. And a solid arrow from a transmitter to receiver means that it is in the communication range. So, with that in mind, say scenario A represents a perfect spatial reuse scenario where the transmitters do not carrier sense each other and they also do not interfere with the reception at the other receiver. Scenario B represents perfect channel sharing where transmitter 1 and transmitter 2 can carrier sense each other. Scenario C represents an asymmetric channel access condition or a pure exposed node condition where transmitter 1 is able to carrier sense transmitter 2 but transmitter 2 cannot, and it always perceives a clear channel. So it hogs the channel and the TX1 RX1 link is stopped. Scenario D is an extension of scenario C where receiver 1 happens to be in the transmission range of transmitter 2. So as we already said, transmitter 2 always perceives a clear channel. So when there is some ongoing transmission from TX1 to RX1, if there happen to be some transmissions from TX2, there will be collisions and we can see some frame losses at RX1. Scenario E and F represent typical hidden node problems. In the first case, RX1 is in the transmission range of TX2, we see frame losses only at RX1. In scenario F, we see frame losses at RX1 and RX2 because of simultaneous transmissions. Now with these interference scenarios in mind, let us take a look at the triggers previously used. Popular TPC techniques use either signal to noise ratio based or frame loss rate based. Signal to noise ratio provides the advantage of faster convergence. Based on link margin calculations, we can easily converge the transmit power to use. But FLR based, we need probing to find out the actual transmit power to use. So there is a slower convergence factor in FLR based techniques. But the drawbacks here are in SNR based techniques, frame loss rate. In SNR based techniques, the problem is frame losses cannot be identified. So if there is a source of interference that cannot be identified by just measuring signal to noise ratio or in wireless card terms, RSSI alone. In frame loss rate based techniques, it might lead to race around condition. By race around condition, what I mean is, if you are using a pure frame loss rate based technique, you might be in scenario A, then for some reason to make some adjustments, TX2 increases its power to RX2, which leads to scenario E, and TX1 compensates for that, and it might end up in scenario F. But since we are using pure frame loss rate based technique, there is no provision to fall back to A, which is the most optimized scenario here. If it's a pure frame loss rate based technique, this is one disadvantage. So our choice is we use both signal strength as well as frame loss rate measurements. We use signal strength measurements as the primary trigger because it leads to faster convergence, and we use frame loss rate as a good secondary trigger for identifying problems due to interference and mitigating them. Then we talked about using RSSI as the primary trigger, so link quality measurements is of importance. And we use the 802.11h framework, which is an extension to the fundamental 802.11 for transmit power and spectral management capabilities. So this 802.11h framework provides action frames, which are nothing but management frames with specific information elements. So we use the 3 information elements as listed here. The TPC request information element to send out requests from AP to stations. We use the TPC report information element to send back the link margin estimates and certain transmit power values. And finally, the power constraint element to say in our algorithm, the AP also calculates the transmit power for the stations. So you need to somehow convey that to the station. So we use the power constraint information element to do that. Okay, let's take a quick look at the prior work. Prior work can be broadly classified as transmit power control for either ad hoc or WLAN or enterprise or controller-based WLANs. And they can be further classified based on the trigger that they use, as we have already seen. So, to talk about transmit power control for ad hoc networks, they were primarily used for reducing power consumption. So, most of the techniques they use high power for RTS, CTS, exchange link quality information, and then they use optimum power for data. That's how they were doing it. But here, spatial reuse is totally eliminated because of use of RTS, CTS. And there were a couple of techniques which tried to innovate by exchanging link quality information first, either using out-of-band signaling or modified RTS, CTS, and then trying to get some spatial reuse. But they all proposed significant changes to the fundamental MAC. And they also relied on precise interference calculation or precise interference measurements, which were unrealistic. Next, to take a look at TPC for WLANs, first look at the SNR-based solutions. The first two solutions are similar to pure SNR-based solutions. They just exchange link quality information and then they use the appropriate path for transmission. The first algorithm, by SAID, they use their own framework for exchanging link quality measurements. But the second technique used 802.11h for the same. And there was the study by Abdesalim was for variations in RSSI in indoor environments. Through extensive measurements and empirical study, they came to the conclusion that the number of significant power levels which showed significant variations in RSSI was very small, say 4 or 5 in indoor environments. And they proposed an algorithm called online RSSI, which computed the distinct power levels that we can use, and any power control algorithm can use them. Then there was another algorithm which proposed joint power and CCA tuning, but CCA tuning, which is the carrier sense threshold tuning, it is forbidden, so it's not realizable in practice. All these solutions again are purely SNR-based solutions, so they cannot tackle hidden node problems or problems manifesting as frame losses. There are some algorithms which already use both SNR and FLR, but it's just that they didn't tightly couple both of them to arrive at optimal transmit power to use. There was a study of impact of AP density on end user experience. They proposed 4 algorithms, 2 of them rate control and 2 power control. But again, the algorithm PERF is of importance here because it again uses RSSI to converge to the optimum transmit power to use, but they do not leverage the frame loss rate measurements to effect adjustments to transmit power. And there was another algorithm called Miser that used a table lookup procedure, but construction of the table offline by assuming a priori knowledge of interference sources, channel conditions is unrealistic. Finally, to take a look at the FLR-based solutions, the solution proposed by Kishore called Symphony, it uses a number of parameters to identify hidden terminal problems, exposed mode problems, and so on. They use RTS at a parameter called utility of RTS CTS to diagnose hidden terminal problem, and they use expected transmission time to diagnose asymmetric channel access problem. But the problem, they themselves say that there is a dilemma as to whether to increase the power or decrease rate in certain scenarios. If there were a proper SNR feedback, then such decision would have been straightforward. And again, ETT calculation or expected transmission time calculation is again non-trivial, even in the regular case, but the packet aggregation in 802.11 and it becomes very tricky. Finally, about control for TPC for controller-based WLANs, it is pretty straightforward. Centralized architectures, they just grab information from all the APs and they can decide on optimal transmit path to use. So our contribution is we propose an adaptive per-link transmit power control algorithm based on both RSSI and frame loss rate measurements. We have implemented and evaluated them on Atheros 802.11 and boards. And we demonstrate through experiments that it reduces interference, improves channel reuse, and improves the overall network capacity. And it's also incrementally.
Can you explain again what the advantage over Kishore's solution is? You all know that's a well-known.
Advantage of Kishore's solution?
The advantage of your proposed solution over Kishore's solution.
Okay, the advantage of our
So
proposed
you have
solution.
disadvantage, SNR is not used. The dilemma arises whether to increase power or decrease rate in certain scenarios. You're not doing any rate control, right? So you don't have that dilemma. Why do you need to use RSSI?
Why do we need, our solution need to use RSSI? Okay, if there is node mobility, then we can clearly pick up whether the problem was due to node mobility or due to interference. The distinction can be easily made if SNR measurements are done. A change in SNR represents a change in the basic link condition between the transmitter and receiver.
You said SNR
Or RSSI.
So you would say that primarily is the frame rate loss. And then if there is
No, ours is primarily based on RSSI and we make adjustments based on frame rate.
What is the problem with node mobility? I didn't quite catch that yet.
For example, say if the frame loss rate increases in a non-SNR based solution, you will see packet losses. But the source of frame losses cannot be identified as whether they are interference or because of node mobility. Say, but if you have SNR or RSSI feedback, then you can make the distinction that there has been a change in the link condition between the transmitter and receiver, or there is some source of interference in the MR.
But then change in SNR could also be due to interference or it could be due to mobility.
There cannot be a
Only
change in
measuring
RSSI
SNR.
because of interference. Interference doesn't usually cause a change in receive signal strength.
Isn't that an SINR measurement?
But wireless, from our measurements, we couldn't pick up interference using RSSI.
I think the major concern is if you use a frame loss rate only, you cannot solve the risk condition. Because let's say I have got one AP, one client, another AP, another client, right? Then for somehow, they start to interfere each other, then the frame loss rate increase, right? Then if you use the pure frame loss rate solution, you say, oh, I got some interference, I don't know whether or not it's interference. So I got some packet loss. I should increase my power, right? You keep increasing the power. And in reality is, if you can lower your power, both lower the power simultaneously, then you could solve this problem because when the power becomes lower, they will not interfere each other.
No, at least look if the power is lower.
If you go back to the place of
Say if the two links were in scenario A, they were already reusing the channel. And say because of node mobility in RX, say if RX2 moves closer towards TX1 or it has moved farther from TX2 and it increases its transmit power to RX2, then it can lead to scenario E, where the transmit power is high enough to cause interference at RX1. And again, if this link is using transmit power control, it will compensate by increasing its transmit power, which can result in a pure hidden terminal scenario where the APs
Didn't you already say result in a
hidden terminal scenario where the APs or the transmitters are hidden from each other, but the stations can listen to both transmitters. So in this case, if it is purely frame loss rate based, then there is no way to get back to scenario A. Because
That doesn't get better by having both users lower their transmit power.
Why is
Because the fact is when they both transmit, they have interference, right? Your SINR is about 0 dB. And if only one of them transmits, the transmission would be better and more reliable if you use more power.
no? So here basically is APA and AP's clients very close. The APB and APB's client very close. But APA and APB are far enough. So for the channel reuse, it's more like the cellular network.
Yeah, but
You have two
the fact
sets.
is it's the relative distances that when they both
Right.
transmit gives the dominant transmitter who's closer to the receiver a much stronger signal. The fact is then the SINR will be roughly about, whatever it is, whether the transmit power is high or low. Changing the transmit power doesn't change.
So basically the SNR is unchanged.
The SINR is actually.
The SI,
Yeah.
Yeah, so here changing transmit power doesn't make any sense, true, but if you are just monitoring frame loss rate measurements, then the natural reaction to frame loss rate increase would be to increase transmit power. So it doesn't make the situation any better.
Yeah.
So you want to get back to the more optimum or the optimal case where you want to still operate at lower power. So that is not possible in pure FLR based scenario or techniques.
No, but I didn't understand something. So what is that you want? You want to you want to make the transmission more reliable. So basically you want SNR to increase, right? So if you're decreasing by 10 dB both transmissions, the SNR doesn't change, but 1 AP. So why do you say that you want to decrease the transmission power?
the thing is, when you look up the power, these two interfere each other. They would not transmit simultaneously
So you want
because they have the carrier sensing, right? So A and B would not transmit simultaneously. It's more like a cellular network. So basically, what you want to do is you want to shrink your cell, right, and also lower your power. Then you can increase the capacity.
By lowering the transmit power, we still guarantee that it's not like just going to the smallest possible, minimum possible transmit power. As we already mentioned, the transmit power that is decided by RSSI measurements ensures a certain SNR. So it ensures a certain sensitivity for a target data rate. Say in our case, if negative 61 dBm is the sensitivity for 130 Mbps, then we don't reduce the transmit power so that it goes less than negative 61 dBm. You at least maintain the conditions for transmitting at a target data rate. So instead of, say, the decision was 5 dBm, you still don't want to operate at 15 as a result of FLR measurements. You still want to operate at 5.
That's why it still pick the target rate as the highest data rate. It's more like, you and I are talking in this room and somebody talking in the other room. If we're both shouting, right, nobody can hear it. But if both lower the voice, they can share.
I
I guess what
disagree.
we're talking about is that the scenario where the SINR is already good enough,
Right.
but the total power is so high that your carrier sense is triggered.
So you're not
Even
changing.
though your SMR would be good enough to transmit in parallel. And
So on the other hand,
in a
it's
sense, your
like
carrier
the
sense,
opposite
now
situation.
by lowering our powers, we can maintain the same SINR, but operate below the carrier sense threshold. Then we can
Okay.
transmit in parallel and we can double the.
But he also
capacity.
described earlier the
Yeah.
reverse situation, right? Like a hang, right, which is
Right.
that somehow that there's a kind of a hidden terminal effect.
Yes.
That
Right.
raising the transmit power, right, will trigger carrier sense, and you won't be injured by the simultaneous transmission. You'll now share the channel. I mean, I think that's what I heard.
I guess that's the
Right.
part I still don't fully understand. And if you if that's the case, why do you have all these packet losses?
Okay, I'll explain the scenario once more real quick. Okay, we are talking about a scenario where they are perfectly sharing the channel in scenario A. For some reason, TX2 increases its transmit power to RX2. It can be due to node mobility, or it can be due to the fact that the link is bad and the power control mechanism again kicks in by using the maximum transmit power first and then less. So it might cause interference at RX1.
Which scenario are we on now?
In scenario E.
E.
Yeah.
From A,
From A to E. From A, there has been some situation in TX to RX2 link that caused an increase in transmit power at TX2, and that has started interfering with RX1. Now, TX1 will try to compensate for that loss by increasing its transmit power if it's a pure FLR based technique. If you see frame losses, you increase transmit power. So now, if it moves on to condition F. Now, say if the situation in TX to RX2 link is solved, and there is a possibility of going back to the smallest transmit power and going back to the same condition A. But if you are always using FLR based technique, you cannot ensure a synchrony between the two links, right? You cannot just assume that they both will reduce their transmit power at regular intervals and you can go down to the smallest transmit power possible. So they're assuming there is no synchrony between the two links. How do you get them back to position or scenario A? But if you have the RSSI feedback, you clearly know that, okay, what I'm seeing is a pure interference problem. Let me just try to go back and try using the smallest possible transmit power and see if the solution works. The provision is available if we use RSSI, but with FLR, that knowledge is not available. Okay, so the proposed TPC solution here has 5 major tasks. The first task being link quality measurement. As we already pointed out, we use the 802.11h framework and exchange TPC request reports and power constraints to do that. And a green solid arrow indicates an input to that particular block. So here the link measurements serve as the input to the power estimation based on link margin block. So here we calculate the transmit power purely based on link quality measurements. And then there is also simultaneous frame loss rate estimation going on in the transmit path at each transmitter. And then the basic power, or say the link margin, power estimation based on link margin blocks provides the basic transmit power for adjustment here. We always adjust starting from the power decided based on RSSI measurements. You either increase it or decrease it. And same is the case on the station side. And finally, you need, with both the power estimates in hand, you need to decide how you are going to affect it to the wireless card. So now to take a detailed look at each of these blocks, link quality measurement, the AP sends out 802.11h TPC requests periodically in our implementation every 100 milliseconds, 10 times a second. So whenever a new station jumps in, it starts transmitting TPC requests to that station too. On the station side, what it does is once it receives a TPC request, it calculates the link margin. Link margin calculation here is straightforward because the target data rate in our case is the maximum data rate. So we know the sensitivity value corresponding to it. The received power and sensitivity is subtract to get link margin. Embed that in the transmit TPC report element. Also mention what transmit power you are currently using and send it back to the AP. That's all the station does. So now, once the AP gets the TPC report with the link margin and the station's transmit power, it can calculate the transmit power that it needs to use on the downlink to that particular station. And it can also calculate the uplink transmit power for that particular station. That is possible because the station has informed you of its transmit power. We have the received power ourselves, so we can easily calculate what the uplink transmit power is and send it to the power constraint information. Now, FLR measurement and power adjustment of the AP, what we do here is, as I already said, constantly we keep monitoring the frame loss rate in the transmit path. And whenever the frame loss rate is greater than a particular frame loss rate threshold, which is 7% in our case, because 822.11 standard specifies 10% as the threshold for sensitivity measurements. So at a particular received power, if your frame loss rate happens to be greater than 10%, then you need to use a lower rate. That's what it specifies. That's how they calculate the sensitivity values in 822.11. So we use a conservative estimate of 7% rather than operating on the limit at 10%. So whenever the frame loss rate is greater than the frame loss rate threshold for a particular period of time, we need to ensure that it is a continuous source of interference and not just some sudden glitch in on the link. So once it's greater than the threshold for a certain period of time, we increase the transmit power by P delta, and here P delta is PD is 2 dBm. We just bump up the transmit power a bit more. And if it's the other way around, if it has been constant and if it hasn't increased, we try to bump it down.
So what's the circuit period of time?
It's 2 seconds. 2 seconds for an increase and 5 seconds for a decrease. Those were empirically determined to be good estimates.
Okay, does that mean you can do it how many packets you actually transfer?
Yeah, actually there is a variation for this mechanism where we can use a window of frames rather than time. There is again another variation in implementation. As you said, if there is a constant.
Your implementation choice is to
yeah,
use 2
one
seconds and 5 seconds and just however random number of packets you send it interval, you calculate the frame loss rate based on.
Which in this case is the same because the rate is constant, so the number of frames in those 2 or 5 seconds is the same, right?
No.
Yeah, it depends on the load, as in how much traffic do I have to send. We use CDR traffic for our tests, so it doesn't matter in this case. But as you said, it's better to have a window of frames instead of time. That will give a more accurate estimate.
I didn't say it was better.
I feel it's better. Okay. On the station side, it's again the same, except that it's measured on the uplink, obviously. Again, we use the same timer variables. Whenever a power change is effected using FLR measurement and a flag is set, so now how do we affect the power changes? We have both the power estimates. How do we affect it with the card? So if we define 2 modes of operation. One is pure RSSI mode, and the other is RSSI and FLR mode. So in the pure RSSI mode, you set the transmit power that has been decided only based on RSSI. And if you don't receive TPC reports for a certain amount of time, you just go on to the maximum transmit power to counter the effect. But in mode 2, we have 2 power estimates. So we always choose to use the maximum of the 2 because PRSSI also serves as the reference for PFLR. As we already said, that's the transmit power which we use as reference to either bump up or bump down. So whenever the update flag has been set or whenever the TPC timer expires, here, which is every 1 second, we effect a change in transmit power, which will be the maximum of the 2. The same is the case in station. It's just that the power constraint is received from the AP. We don't calculate it in-house in the station. So if it stops receiving power constraint from the AP for a certain amount of time, we increase the transfer power to the maximum. That is in mode 1. In mode 2, we choose to set the maximum of the power based on RSSI measurements, which is sent by the AP, and the power calculated from FLR measurements. So these are the parameters, values that we have used in our experiment, as I have repeated many times. The maximum and minimum are 15 and 1 dBm. Again, coming back to the granularity of power control, I said that, okay, I will see this. Whenever the transmit power difference calculated is greater than or equal to 2 dBm, we affect the change to the card. This is because there have been studies in the past which have shown that RSSI the number of power levels that creates distinct RSSI variations in indoor environments is 5 to 6. And even in Symphony and many other rate control algorithms, they choose to use 3 dBm as the threshold for affecting transmit power control changes. We use 2 dBm based on empirical measurements, as this has proved to be a better estimate to use. Again, the DPC request is sent out every 100 milliseconds. Power adjustment is done every second or whenever the update flag is set based on frame loss rate measurements. And the expiry timer here is 5000 milliseconds, which is if I don't receive TPC reports for 5 seconds, or if I don't receive power constraint for 5 seconds in mode 1, I just go on to maximum power. So that is what the TPC expiry time is. The threshold, as I said, is 7%, and the up and down time is on 2 and 5 seconds. Again, the variation of the algorithm is to use a window of, maintain a window of transmission status of packets and then decide what the frame loss rate is. The reason for, we talked about 2 modes and why we need 2 modes and why we need to constantly switch between the 2. The switch from mode 1, which is pure RSSI based, and mode 2, which is both the triggers based, is pretty obvious. If you want to account for frame losses, you would want to switch to mode 2. And mode 2 to mode 1 is to counteract the race around condition. So you might want to periodically check that if you have entered a race around condition or not. So you unconditionally go back to a pure RSSI mode and make sure that the problem is solved.
Can you say something more about this race around condition? Can you make an example? So what is happening there?
Oh, as I already said, from scenario A, there is a problem that it moves to scenario E where one link increases its transmit power. And the same happens to the other one, they constantly keep increasing it. If we just monitor FLR here, the FLR trigger constantly points out that there is some problem just increasing the power. So you constantly keep doing it, but you want to stop doing it at some point in time. So you switch to mode 1 where you ignore FLR triggers. If the problem is solved, it's fine. Otherwise, just continue to do that. Next is the experimental results and discussion. We implemented it as applications running on 802.11 APs and stations. These 11 Atheros board evaluation boards are similar to our orbit boxes, except that they are very much less powerful. They just have 200 megahertz processor and they have flash memory system running embedded Linux. We couldn't have traffic generators running on these devices, so we had to use hosts connected through 100 Mbps Ethernet to the access point and station to generate data. And they also had a major drawback. These evaluation boards came with 100 Mbps Ethernet ports on them. Even though the wireless card is capable of greater than 100 Mbps transfers, the ports were 100 Mbps, so we pushed not more than 94 Mbps as our offered load. And that is the default offered load unless I specified otherwise. The duration of the experiments were 15 seconds each and they were all connected to 5 gigahertz band.
So you said that in 5 years there are 24
non-overlapping channels.
But most of them are used for?
Radar. In Europe, all devices operating in the 5 gigahertz spectrum, they need to have this radar compliancy, or they call dynamic frequency selection compliancy. If they see radar sitting at a particular frequency, they hop on it.
Okay, so how many channels do you have?
So we have 14, 4, and 5 at the back. So we have 9 to operate with non-DFS channels. Non-DFS channels are just non-overlapping. Yeah.
So what I totally miss is how do you use this multiple channels? How do you pick these channels?
Oh, okay. For each
one,
experiment,
I guess.
yeah, we just pick only one. All I'm saying is that These devices usually come with default settings and end users rarely change them. If we can just put NetStumbler and see in an apartment building, everybody will be on channel 6. So
Things are changing because
yeah,
everyone knows that it's been 2 years to figure.
yeah, but that basically is the need for adaptive resource management. You should be able to switch channels and either use power control or dynamic frequency selection to make sure you are
So
in
why
control.
attacking this problem rather than selecting a channel?
We also implement our algorithm how to select the guys to check. So here, basically, if in very dense deployment, right, so you have a lot of APs, so you may end up, some of them must share the same channel.
I understand.
So there another algorithm for the channel selection, also the planning to run.
And all the experiments are conducted in 1,000 corporate research. So the first experiment is to demonstrate the power reduction that can be achieved by using the power control algorithm that we have proposed. The position of the AP is represented by the triangle, and the stations are constantly, they are moved from positions A, B, C, D, and D, just increasing distances from the AP to show the effect of distance on the transmit power decisions. So the channel we used for this experiment was channel 56. Basically, the channels we choose for each experiment were by determining whether any other devices were operating in the channel or not, because there was an enterprise WLAN settings and they constantly hop channels. So we had to ensure that we were not operating the same channel. So there might be different channels for different experiments. So here we can see from the graph that based on RSSI estimation, the y-axis on the left represents the throughput and the y-axis on the right represents the transmit power used in dPm. The maximum power, which is default, I have not shown in these graphs. So the first bar represents the throughput with maximum power, which is 15 dPm, and the second bar shows the throughput with the TPC power. Let me just call it that, TPC power that we calculated. And the third bar actually shows the actual value of transmit power used, or the average value of transmit power used. From the diagram, we can see that for even stations up to 70, separated by 70 feet from the access point, we can achieve up to 60% reduction in transmit power based on RSSI estimates. So this experiment just goes on to show the power reduction capability of the algorithm.
So what was the middle bar? The gray bar?
Oh, this is the throughput with transmit power. The first bar represents the throughput without power control, which is the maximum transmit power. Second bar represents the throughput with transmit power control.
Okay.
And the third bar represents the actual transmit power used.
Okay,
Transmit power
well,
control.
where would the transmit power be if you didn't use the transmit power control algorithm?
It will be 15 dBm, which is maximum. So we'll have to refer to the right hand side y-axis. The right.
It'll be up on the top of the.
Yeah, the y-axis on the right represents the transmit power used in dBm, this is 15 dBm.
Maybe you
So
better
it's like-
give one location, so then explain this
Okay,
bar for
so
one
for location E, location E is at 71 feet from the access point. First, when we use the maximum transmit power, this is the throughput that is achieved. And with power control, this is the throughput that is achieved, but the actual transmit power used is shown in this one.
So it's
It
like
gets worse
60
with
dB
your
too
power.
high. So
Sorry?
you save like 60 dB.
Yeah,
Are you saying the throughput becomes worse with your transmit power control?
no, throughput
The
doesn't get
throughput is almost the same. If you
throughput
take-
doesn't get worse with
It's
transmit power.
almost the same, but
It's a little
so it's worse, right?
It should be a little worse.
It should be just a little.
Okay,
I would expect to be better because you are avoiding interference. That's
No.
Yeah,
Here there's no
There is
interference.
no
There's no
interference.
interference.
Okay.
Sorry, I didn't mention that.
Okay, you're saying you can decrease power without jeopardizing the throughput, without impairing.
Right.
What is channel 56?
5.28 gigahertz.
So are there really that many channels? Sorry, I said something.
No, I think it's
No,
it's
no, it's
someone starting from the
Yeah.
36.
It's
That's
not
36.
continuous. They have 40, 44,
Yeah,
50, then 56, then they have 100 something.
Yeah, maybe I specify
Or
the
5 megahertz.
It's like the TV,
All right.
the TV bands convention.
Is it, when you say the TV band convention, what do you mean?
The 5-6 megahertz for and this
So
870.
it doesn't really correspond to what frequency old channel 56 UHF was on. You're just saying it's a
no, it's just analog.
a
It's just
5 megahertz jump when the things are actually
Yeah.
wider.
I guess it's 56 ISM.
Okay,
Starting reference or ISM.
Go ahead, please, yeah.
Okay, the next experiment is to show the per station power control capability. We didn't have enough evaluation poles in hand, so there were just 4 of them. So we had to devise a separate experiment to show the per station power control capability, where we decide, choose the optimum transmit power for each of the associated stations based on link quality measurements. So again, AP is represented by the triangle. Station 1, 2, and 3 experience good, fair, and bad channel conditions based on distance of separation. So you can see station 1 is 26 feet from the AP, station 2 is 52, and station 3 is 80. We used 3 simultaneous UDP streams, 15 Mbps each, just to emulate high definition video traffic. This was just to show the per station power control capability. So the graph here, what it represents is the first 2 bars represent the RSSI measurements, and the next 2 represent the actual transmit power used. So this RSSI is normal. It's a normalized RSSI. So you subtract the received power from noise floor to get a positive number. So that's why the axis is positive. So negative 61 corresponds to 40 with a noise floor of negative 100. So here we can see that we are operating at way too much higher power than it is necessary. So based on link quality measurements, you can pull it down to as low as 40. So that the RSSI is just 40, and you can still ensure data transfer at the maximum data rate possible. So this is the maximum transmit power used, which is 15, and the transmit power used for station 1 was 1 dBm. For station 2, it was 6 dBm, and station 3, since it was already experiencing a bad link, we did not want to complicate matters even further. So the power control algorithm just decides to use the maximum transmit power for that particular station. So the next experiment is to demonstrate the increase in spatial radius. There are 3 links of interest in this experiment, and only 2 of them are in the experiment at a given point in time. First, we study the interaction between link 1 and link 3, and then we study the interaction between link 2 and link 3. So when link 1 and link 3 operate at maximum transmit power, they basically share the channel. So this experiment just goes on to show the transition from scenario B to scenario A. If they are in scenario B and if you use transmit power control, they will go to scenario A where they achieve perfect spatial reuse. That's what we want to show in this experiment. So, yeah. When they are both operating at maximum power, they share the channel, and the throughput is close to 120 Mbps, which is the maximum throughput possible with the MAC overhead. So, but when they operate at the TPC power that has been calculated based on link quality measurements, we can see that there is a significant increase in network capacity, up to 60% increase. Here we cannot see the actual gain that we have achieved because of the 100 Mbps bottleneck, as I mentioned earlier. So here it caps at 185 Mbps because of the limitation placed by the 100 Mbps Ethernet ports. The interaction between link 2 and link 3 is again similar. First, they use maximum transmit power, they share the channel. And when optimum transmit power is used, there is significant spatial.
Why does your Ethernet board cap it at 60% improvement?
Excuse me? Why does it
Were
cap?
you saying that your Ethernet board caps it at 60% improvement?
Oh no, that's because the maximum that I can push is 94. So that's the reason I
Which is
can.
also the case in the experiment that does not use power transfer.
There's no use for, yeah, again. The first
If you
experiment.
now use two clients running in parallel with two access points, you assume you can get to that limit.
Which would be 100, 230, 240 Mbps. It's like 120 on each link. First,
I thought 95 is the max. Was it 85 or 95
oh,
is the
no,
maximum?
theoretically, 120 should be possible over a single link.
Right, but practically,
But practically here, maximum is 94 over a single link.
94.
Yeah, so the maximum
So
that we
with
can
power
see.
control, you should be able to reach 94 times 2.
Yeah. Which is
Majority
188.
got about 180.
I see. But why is it only a 60% increase in network capacity and not a 100% increase?
Oh no, 100% increase would be, say, okay, I'm talking about aggregate capacity. Aggregate capacity here is 120 Mbps because I'm using two links to pump data. They are sharing the channel and they can go up to, it's,
Oh, I see.
okay, yeah.
You're comparing two transmissions versus one transmission, but he's comparing two transmissions with power control, two transmissions without.
Got it, yeah.
So this next experiment, I'm sorry about the graph. The next experiment is again a demonstration of spatial reuse. Here we just wanted to find out the breakpoint, or we wanted to show with respect to distance, what is the distance where we start to see an increase in spatial reuse. And the ABs, the two pairs, the first pair is always located at position 0, which is represented by a star. And then we constantly move the other pair around and see what the gain is. But to up to 86 feet with 3 walls, again the maximum line of sight separation that we could get was 109 feet. So we had to rely on obstacles to translate to larger distances. So approximately at 97 feet with 4 walls in between them in an office environment, we could see a drastic improvement in spatial reuse. Unfortunately, more granularity in terms of this graph couldn't be obtained.
So in P5 is the same point?
Oh, I'm sorry, P5 shows an increase. This is the breakpoint.
Oh, okay.
Okay, this is the final experiment which demonstrates the use of frame loss rate trigger in the or behavior in the presence of either cooperative or non-cooperative interference. Say link 1 here is the link of interest and link 2 is the interfering pair. It always operates at maximum power. Link 1 first uses maximum power, then uses RSSI based transmit power, and then uses RSSI and FLR based transmit power. So if they just use maximum transmit power on both links, they share the link, and the throughput, aggregate throughput is around 120 Mbps, which is 60 plus 60 here. This is the transmit power use, and I'm sorry. Okay. In the next graph, we can see that if we are using mode 1 TPC, which is based only on RSSI, link 1 uses the lowest possible transmit power, which is 1 dBm. Link 2 continues to operate at maximum power, but there is a disparity in terms of channel access. When we use frame loss rate trigger, we can see that link 1 has picked up frame loss, because of the frame loss rate trigger that we have on AP1, it has picked up the disparity in terms of channel access, and it has increased its power to compensate for the losses. So it decided to operate at 9 dBm on an average to counter the effects of a negative effect that link 2 had on it. Again, in this experiment, this represents a switch from scenario B to scenario B. Here again there was link losses on receiver 1, That's how the frame loss rate trigger picked up, and the power compensation resulted in scenario B, which resulted in channel sharing. So, in conclusion, we proposed an implementable and incrementally deployable TPC solution that tackles hidden node as well as asymmetric channel access problems, which manifest as frame losses. We implemented it on 802.11 hardware and evaluated the performance. And as well as suggestions for future work goes, the station side power control couldn't be implemented because of the unavailability of an IOPTL call to effect the transmit power change. The usual way that we do it for everyone who use WLANs right now, IW config 880 DXPAR, you can set that, but that leads to a service disruption. So we didn't want to go ahead with that. So station side power control, the framework is in place, but the change in affecting the transmit power was not possible because of the unavailability of an IOPTL call. Again, pure exposed node problem, which is a special case of channel access asymmetry, cannot be identified by our algorithm. Symphony uses ETT to do that, but it's a very tricky metric to compute. So we need to investigate into mechanisms to identify exposed node problems. Again, per station power adjustment based on frame loss rate. Right now, we don't have the transmission or the frame loss rate for each individual stations. We have for all the downlink transmissions. So the adjustments have to be made for all the clients and not on a per client basis. If the statistics are made available, usually the wireless cards don't provide those statistics. If they are made available, then per station power adjustment can be effected. Again, fire rate control, if it is jointly done along with rate power control, we can achieve further reduction. But as we already see, the margin is just 15 dBm. So if we do power control, the difference in RSSI would be like, RSSI requirements would be like say 20-25 dBm, which we cannot reflect in terms of change in power control, but still in certain scenarios it might prove helpful. Again, large-scale experiments and mobility experiments couldn't be done because of the evaluation goals. When 802.11n comes out as a proper standard and when there is a reliable open source driver available, then we can implement it on cards, on laptops, and mobility experiments can be done as well. Thank you. Any questions?